All right, let's dive into a piece of technology that literally changed the world. Today, we're talking about the first functional laser ever built, the Ruby laser. We're going to break down exactly how a beautiful gemstone was turned into an incredibly powerful beam of light. So how do you even do that? It sounds like something straight out of a comic book, right? But this is the exact puzzle that Theodore Maiman cracked way back in 1960. He figured out how to take a simple pink ruby and get this powerful focused beam of light out of it. And you know what? The ideas he used are still the bedrock for almost every laser out there today. Okay, before we get into the nitty-gritty of the ruby itself, we need a kind of universal blueprint. It turns out that any laser, and I mean any laser, from the tiny one in your phone to the massive ones that cut through metal, is built on three basic, absolutely non-negotiable parts. So what are they? First, you need an active medium. This is the stuff, the material that's actually going to create the light. Second, you gotta have a pumping agent. Think of this as the power source that gets the active medium all energized or pumped up. And third, you need an optical resonator. This is basically a fancy name for a pair of mirrors that traps and amplifies the light. And here's where it gets cool. Let's see how that blueprint fits our ruby laser. For the active medium, it's that pink ruby rod, but more specifically, it's the chromium ions mixed inside. The pumping agent? That's a super bright xenon flash lamp coiled around the rod. And the optical resonator, this part is just genius. They simply polished the ends of the ruby rod and coated them with silver to act as the mirrors. How efficient is that?
So, what did this history-making device from 1960 actually look like? Let's pull it apart, piece by piece, and see how Maiman put it all together.
All right, here are the specs you'll want to know. It's what we call a solid-state, three-level laser. Now, the active medium isn't just pure ruby. It's an aluminum oxide crystal with a tiny amount, just 0.05% of chromium ions mixed in. That chromium is the secret sauce. The pump, like we said, is that coiled xenon lamp, and for the mirrors, or the optical cavity, one end of the rod is fully silvered, a perfect mirror, while the other end is only partially silvered. That's the escape hatch for the final laser beam. Okay, we've got the hardware down, but how does it fire? Let's trace the journey from a simple flash of light to a powerful laser beam. It all happens incredibly fast, right down at the quantum level. The whole thing kicks off with a process called optical pumping. The moment that xenon lamp flashes, it just floods the ruby rod with intense light. The chromium ions soak up that light energy, and it literally kicks their electrons from their normal lazy ground state, we'll call that E1, all the way up to a really high excited energy state, which we'll call E3. And here's a key number, especially if you're studying this for an exam. The chromium ions are picky. They're tuned to absorb a very specific wavelength of light from that flash, right around 5,500 angstroms. You can think of it as the exact right key needed to unlock that first big energy jump. But here's the thing. That high E3 state is super unstable. Almost immediately, we're talking nanoseconds, the ions drop down to a middle energy level, E2. And this is a really important detail. When they make this drop, they don't release light. It's what we call a non-radiative transition. That energy just gets released as tiny vibrations in the crystal, basically as heat. Now this middle level, E2, is the absolute heart of how the ruby laser works. It's a special kind of energy level called a metastable state. Think of it like a little shelf or a waiting room where the excited anions can hang out for a relatively long time before they drop the rest of the way. This holding zone is what makes everything else possible. Because those ions can collect in that metastable waiting room, the constant pumping from the flash lamp lets us achieve the single most important thing you need for a laser, population inversion. This is the magic moment. It's a condition where you actually have more ions sitting in the higher energy metastable state, E2, than you have down in the low energy ground state, E1. So think about it like this. Normally, everything in nature wants to be at the lowest energy level possible, right? Like a bunch of balls rolling to the bottom of a valley. But here, with that intense pumping, we're forcing the balls up the hill and getting them to pile up on that shelf halfway up. It's a totally unnatural, top-heavy system, and it's primed and ready to go. And that's when stimulated emission takes over. All it takes is for one of those waiting ions to fall from E2 to E1 by itself, spitting out a photon of light. If that photon happens to hit another excited ion, it doesn't get absorbed. Instead, it stimulates that ion to fall and release a second perfectly identical photon. Now you've got two photons, and they hit two more ions, making 4, then 8, then 16. It's a chain reaction, an avalanche of identical photons all bouncing between the mirrors, getting stronger and stronger.
And that light has a very specific fingerprint. That energy drop from E2 down to E1 always releases a photon with a precise wavelength, 6943 angstroms. This is what gives the ruby laser its signature deep red color. This is the beam that becomes strong enough to finally blast through that partially silvered mirror.
Phew! So, we've walked through all the quantum mechanics. But what's the end result? What kind of beam of light actually comes out of this amazing gadget?
Now, this is a super important point to remember. The ruby laser is a pulsed laser. It does not shoot a continuous, steady beam like you might see in a movie. Instead, it fires in really short, really intense bursts of light, and this is a direct result of its three-level energy system.
So why the pulses? Well, it all goes back to the lifetime of that all-important metastable state. 3 milliseconds might sound incredibly fast to us, but in the atomic world, that's practically an eternity. It's just long enough to build up that population inversion. But once the laser fires, the ground state gets filled up again, and the system has to stop, recharge, and get pumped back up for the next powerful shot.
But the reward for this pulsed operation is jaw-dropping power. By dumping all that stored-up energy in a fraction of a second, the peak power in a single pulse can hit 100,000 watts. That's an incredible amount of energy focused into a tiny, tiny point.
Okay, that was a lot of info. Let's wrap this up by boiling it all down into the absolute key concepts you need to walk away with. If you're studying, this is your moment.
This slide is basically the whole story in a nutshell. Ready? You start with optical pumping using 5500 angstrom light. This allows ions to pile up in the metastable state. That pileup creates population inversion, which is the necessary condition for stimulated emission, the chain reaction, to happen. The result? A pulsed, high-power, deep red beam at 6943 angstroms. Got it? Good.
And it's always worth remembering the historical context. This wasn't just some theory on a blackboard. This was a real machine, built in 1960, that kickstarted the entire field of laser technology. It was the first of its kind, and it's the classic textbook example of a three-level laser system.
So, I'll leave you with this final thought to chew on. We know this three-level system is inefficient and can only produce pulses because the ground state gets clogged up. So what kind of change would you need to make to the energy levels to allow for a continuous beam? It's a great question to see if you've really got the concepts down. Thanks for watching.